It's very small, but I guess we'll have to do since it's so close. Okay. So now. How do you get this projector to connect to?
Is there a favor if you want to have it before?
Oh yeah, I had it before. It's not very clear. Yeah. Okay. So. Okay, so I've plotted the what the time dependence is for a bunch of coherent state. And the coherent state was a different number of expected photons there. Okay, so for this one, there's very little expected photon. You see the thing is pretty chaotic. Okay, but if you look closely, what you'll see is, okay, so we start with the initial state. Okay, and then the population inversion collapses down to 0 at roughly, okay, I'm going to tell you that this is roughly like 2, okay, over here, but maybe you cannot read this scale. And then afterwards, there is something, it goes up again, okay, down, up, okay, but this is quite chaotic. This is more, this collapse and revival phenomena is more apparent when you look at this figure over here, where we have put in more, let me explain these numbers later, where we have put in more expected number of photons into the coherent state. Okay. You see that the field collapses first, there's no population inversion for a while, and then the population inversion revives. And then it revives again, but then it's wider. Okay. Over here it's the same thing, but even with more number of photons, you see that it collapses at about the same time at 2 here. And then it goes up again, but then these revivals are more separated. Over here, it's the same thing. The first revival is even more delayed when there's more photons. Okay. But as you see, the first collapse is pretty much all localized to around here. So this is what we get.
Is this the same theory behind the MRI fault echo pulsing?
The what?
The MRI echo formation?
MRI echo formation.
So when you
I'm not familiar.
okay, so basically you get the same sort of pulse revival at some point after the signal decays first.
Okay.
I was wondering if this is the same theory.
It could be because what is happening really is if you think about a sinc function, that we get a sinc function by adding a bunch of signs together, and if for the sinc function there are side lobes, and when you basically when you, I guess it's exactly the same.
Yeah, I think it's, the MRI thing is quite different. MRI thing involves many protons.
Okay.
And then you get those protons to precess. And then after you get them to precess, you turn off the exciting magnetic or RF field, then they start to radiate coherently. And then it's called a pulse echo in MRI. But this is just involving one atom. So not a whole bunch of protons.
Okay.
So it's quite a different kind of echoes. The MRI echo is similar to what we did for the two-level system when we did density matrix. Remember there was one where we used coupling of light to two-level atom. MRI is very similar to that. And then it's a coupling of an RF field to a spin-up, spin-down system in the MRI. So this is very different. This is just one atom.
Okay.
And you have this phenomena which is very interesting. It's a cavity and an atom. Okay, so it's quite different.
Okay, so let's come back to these figures later, and now let me show you why they appear. You guys can still see the blackboard, even though it's here. Okay, so that's fine. Let's just keep us just right as this.
You put a paper over it.
Oh, Okay, let me just turn it up.
It's on the piece
Yeah,
of paper.
Just like, turn it away.
Turn it away. I think this is okay. So now, let me tell you that the coherent state can be written in terms of the expected number of photons in a different way. That's more convenient to work with. Okay, so I'm going to write this as e to the minus this thing. Okay, so essentially, what is being done here is simply just you take out you take out a factor from here, okay, and it becomes this factor again, okay. And then there's some algebra there, but let's not worry about that. The coherent state can be written as this as well. So now, what I'm going to do is so for this thing, 2 lambda square root of n plus 1. Okay. This thing, I'm going to do a Taylor expansion of this around the expected number of photons, so around n bar.
Is that T or
Wait, this is t, sorry. So let me expand this, and how do you expand a function like this? So you plug in n bar, right? And then to first order, you're going to get a minus sign, I think, because no, you have a plus sign. Okay, and you take the derivative, it turns into something like lambda over square root of n bar plus 1. Okay. And then this is n bar minus n. Right? Something like this. Oh, no, it should be n minus n bar. And just think about the Taylor expansion. Okay. There is a 1/2. So when you take the derivative, right, this is 1/2 powers, which cancels this. This is what you get. So we separate this into 3 terms. Okay. So this is like 2 lambda square root of n bar plus 1 lambda n square root of n bar plus 1 minus lambda n bar. So now the good thing is only this is dependent on the n, right? So I'm going to turn the cosine into the exponential form, the sum of exponentials. So let me turn the cosine 2 lambda square root of n plus 1 t. This is written as exponent. There's a square root of 1. There's a 1 over 2 factor for it. E to the I. Okay. And this 2 lambda square root of plus 1 t. Plus its complex conjugate. I'm just going to work with this one for now, because everything happens in the same way for the complex conjugate. Okay, so we plug this expansion up into the exponent here. Okay. And that turns into something like, okay, so we get e to the 2 lambda square root of n bar plus 1 t. Okay. This can be taken out of the summation, right? Also, this term can be taken out of the summation. So you have e to the minus I lambda n bar square root of n bar plus 1. Okay. And if I were to work with the summation, I have this over here. Okay. So let's attach that factor, e to the minus r. And there's a 1/2. And then inside of the summation, I just have n equals to 0 to infinity, n bar to the n factorial. And this part just becomes, what's left is just this, right? And notice there's an n here. Okay, so now we can combine the whole thing into some exponential. Okay, so this is e to the I lambda n divided by t. Okay, right? We got the t here. So now, take out this n. Okay. So obviously, this whole thing is going to combine into this whole summation. Okay? This is some kind of an exponential. Okay? So the exponential is exp. Okay. The thing being exponentiated is n bar times e to the I. Okay. Lambda t divided by square root of n bar plus 1. Correct? Yeah. So now let's say for a very short time, so we're looking at the collapse. For the first collapse, which we found to be a very short time for all the n, okay? So when t is small, okay, we can expand this exponential, and let me expand it to second order. So this is roughly equal to e to this, okay? And then turning this expansion goes into a sum, right? And when the sum is on the exponent, it goes into a multiplication, a product, obviously. So this is like e to the I lambda t square root of n bar plus 1 e to the minus 1/2 okay, lambda square t square divided by n bar plus 1. Something like this. Did I make a mistake? No. Okay, yeah, this is right. Okay. So now, what we can do is take this n bar factor. This is again, this is going to cancel this n bar minus thing, right? Okay. And then also, we have, for some reason, I think this should cancel this. Maybe I left there's a mistake somewhere. Oh, I threw out an n bar. Okay, that's why. Now this is right. So this is going to cancel with this one. Right? Yeah. This cancels with this one. Okay? And then we're left with this exponential term. Correct? Alright. Now you think about the complex conjugate. Everything is the same over here, right? Except that we're going to get a minus sign here. Okay? Which still has some cancellation out there. But you're also going to get this real exponential factor, which is a minus. Right? Because regardless of whether this is a plus or minus, the second order is always a minus. Okay? Okay. So even for the complex conjugate part, we still get this factor and the cancellation here. Okay? Cancellation here, and then we have this plus its complex conjugate, which is going to a cosine. Right? So we get, in the end, we can take out a 1/2 lambda squared t squared n bar divided by n bar plus 1. Okay, 1/2 of e to the I lambda square root of n bar plus 1 plus its complex conjugate, and this is just cosine of 2 lambda square root. Sorry, I forgot. Square root of n bar plus 1. So let me just replace it up here. Cosine of 2 lambda square root of n bar plus 1t. Okay, so this is what we get for the rough behavior of the population inversion for small t. Okay, so you notice that it's going to want to do rapid oscillation at the expected number. Okay, expected number of photons. Okay, this rapid frequency. Okay, but the thing is damped by this exponential factor. Okay, so we can look at the first collapse time by looking at when does this exponential factor get small. Okay, and if you remember this thing is just like, if you write this as a Gaussian, there's like a t squared, is lambda squared t squared, and then there is a sigma, which is the what's that called? The standard deviation for the Gaussian, right? So that's just like lambda t, okay, is equal to square root of n bar plus 1 over n bar, and then you need a square root of 2. Okay, so this is like this. This is when the Gaussian falls to 1/3, to 1 over e. Okay, so, and then you can say that, okay, So lambda t for the first collapse, okay, is roughly going to be equal to square root of 2, regardless of n, when n is a large number. Of course, the equation fails when n bar is 0. Right? So for the vacuum case, the zero state, which is the quantum vacuum, this is certainly also a special case of the coherent state. Right? So when we saw that there is vacuum gravity oscillation, that is actually also undergoing this collapse and revival thing, but it's never collapsing. Okay. However, for this one, if the expected number of photons is large, then the collapse is happening over here. So this is why you get this kind of thing. Let me turn that back into that. This is why you have this collapse and revival. And the larger this is, so what we have shown here is that the first collapse is actually quite independent of the number of photons, except when the number of photons goes to 0 or 1. So we get these things. And then the first revival, okay, why does it revive? And what's happening essentially is that you have a superposition of different number states, and each number is going to cause a different Rabi frequency, right? So the atom and the field, what they're doing is they're oscillating at a bunch of different Rabi frequencies that are rather close together. Okay. So the dominant Rabi frequencies are close to n bar, okay, because of this exponential thing. So the dominant frequencies are close to n bar, and then essentially what happens at the first revival is the first time when the n bar and n bar plus 1 or n bar minus 1, when these things become into in phase again. So when are they in phase? Okay. We can write simply so revival is omega of n bar and omega of n bar, let's say the plus 1 state. Okay. Now when the time is such that their difference is equal to an integer multiple of 2 pi. So 2 pi. Okay. And the first one is for k equals to 1. Okay. So this is saying that these two, the difference here, is equal to 2 pi over t. This is saying that lambda t is equal to 2 pi divided by the frequency difference here, depending on the Rabi frequency. Right? So this is why actually we are able to predict when the first revival happens. Okay, notice that over here I predict the first revival is going to occur at time t equals to 10, and exactly at t equals to 10. There's a mistake with this. So this one is happening at t equals to 15. Okay. This one is happening at t equals to 25. And over here, this is t equals to about 30-ish. Okay. But my point is, based on the mean number of photons, we're able to predict when does the first revival happen. And that's why I label these plots with t, but apparently I labeled it wrong, so sorry. Okay, so yeah, that's it. That's for collapse and revival. So remember that the significant thing here is, although in the classical case, if we consider field to be a classical quantity, we get Rabi oscillation. The fully quantized theory tells you that you do not get Rabi oscillation for a classical field, in the sense of we're using a coherent state to mimic a classical field, but that doesn't give you Rabi oscillation. It gives you these collapse and revival. And the reason is that in the fully quantized version, the field still has quantized nature. Right? So the different ends, they oscillate at different frequencies, and those oscillators, when you sum up a bunch of different frequencies, you're going to get these kind of like beats. Okay. This is what's happening here. Right. So I guess we stop here, and then next time we pick up with the thermal state. and then we're going to talk about showing the cats. And we're going to talk about off-resonant. Okay, our next